Hello. So for exercise number 12, we are going to discuss the representation of sound by image through analysis of sound frequencies. So there are two main ways to visualize sound. There are more, but I would say that there's two main ways. One is through the time domain, which is very usual when you open any audio program. This is the most common visualization you see. So in the time domain, what is shown to us is the loudness amplitude of sound wave changing over time, right? But another way to represent represent sound is to analyze its component frequencies. Our listening range goes from 20 hertz to 20 kHz or 20,000 hertz, where the lower pitch sounds produce a kind of a lower frequency, so they change the air pressure with less frequency than the higher ones. So this kind of low pressure really has a kind of physical impact. If you hear it, you can really feel the change of frequency and pressure. Whereas in the higher frequencies, you don't feel it so physically, but of course you can hear it. But the human range is limited to roughly, it changes person per person, but roughly between 20 hertz and 20 kHz. And one common way to analyze frequency is to use an algorithm called the fast Fourier transform, right? So I obtained this information through a link which I can provide you later. I'm showing this from this link. So, for example, there are pages online where you can actually listen, right, to the different frequencies. So, for example, this is 440 hertz, but I can really change this. So here you see the lower frequencies. And here the higher frequencies. At a certain point, you are not just limited by your ears, you're also limited by the capability of your speakers or your headphones to reproduce this. In my case, I think my speakers started to not display the audio after a certain point, but I was already having trouble hearing it. So with this brief introduction, let's go to Xcode, import a sound file, and then analyze its frequencies, right? So I went to freesound.org and I obtained this sound. It's a little bit cheesy, but I like it because it has this kind of traditional drums, bass, guitar kind of approach, where you have the low end, you have the mid end, and you have some high end. Not much in this file, but I didn't want to use a copyrighted file, so I used this one, and actually it's this link here. Okay. So let's open, I will open the project generator, and I'll create a new project. So I will target my usual folder, and I will call this exercise 12 sound frequency. Okay, sound frequency, and generate and open in IDE. So the first thing I need to do is to import to load my sound file and to play it, just to make sure it's playing. So I have the sound file here already, and I will add it to my apps, SoundFrequency, bin, data, so I will put it here, and I'm going to select all this, and I'll start coding. So this is not new to us. We did a similar thing in the previous exercise of sound player, and I'm going to call this my sound, for example. And in setup, I'm going to say my sound.load, and what are we going to load? We're going to load this file here. Okay, great. And now it's very short, so I want to loop it. I'm going to say my sound. Again, we saw this in the previous exercise. Set loop to true. Actually, the code completion is not kicking in yet. Just checking if I have any typo. No, just not kicking in yet. Hasn't. Oh, now it's showing you have a color coding and these kind of things. I have a semicolon missing here, and now I'm ready to go. And I don't need this panel there. So actually, I can play it just from just in the setup. Then it kind of plays by default. So let's run it and see what we get. So for this exercise, what I want to do is create a graph that shows my frequencies. So I can have a certain amount of frequencies that I can analyze, and I can map that information from those frequencies to, I don't know, a rectangle that will go up and down in the screen. So then I have kind of a bar chart, animated bar chart of the frequencies. Right? So to do that, we will use, while this compiles, we can actually we have time to go to openFrameworks, documentation, sound. And here we have in sound player, we have something called of sound get spectrum. So it returns FFT analysis of the sound. Each band will be represented as a float between 0 and 1, and you can get a maximum of 512 bands. Okay. So Xcode is still compiling. So I would recommend that you have multiples of 8 for the frequency. So I got to notice that something is happening. So let's, yeah, here we go. Not much is happening. You will notice that when MP3s loop, there's always a little gap between the end and the next time it plays. Or to my ears, there seems to be a little, like tiny little gap that WAV files don't have. To my ears, there's always a little. But anyway, for this purpose, it doesn't matter so much. So the playing part of the sound is happening. Now we need to go and display our graphics that we want to use. So the first thing you need to decide is how many bands do you want to draw, right? How many frequency bands? So frequency bands, this is the term for the interval of frequency. So you have from 20 hertz to 20k hertz. By the way, the unit hertz means times per second. It's almost like a FPS kind of unit, right? Pardon, or frames per second kind of unit. So to draw, let's create here. So what we need is an integer n bands, right? So let's define an integer n bands or num bands as you want. As you want. Let's say that we can start with a full-on 512 bands. That is, which is the maximum that we know how to get. Okay, so that's fine. So where the magic happens is with the code of sound get spectrum. So we can just say of sound get spectrum n bands, and we get the sound spectrum to a float. But note that this float has an asterisk. This in C++, this means a pointer. So in C++ we have, I don't want to go too much into this kind of deep C++, but in C++, again, as I've been mentioning, there's very powerful tools to manage memory. And one of these powerful tools are pointers, that instead of creating variables, each time you create a variable, you're creating a new slot in memory. And if you put information in that variable, from another variable you put into another variable, you're just duplicating information. It's not very sustainable, let's say, approach, especially when you're dealing with sound data, video data, heavier kind of file sizes, let's say, or information sizes. So we have this construct, which is a pointer, which goes straight to the address in memory where and some information is stored. So I like to describe it, I'm not sure if it's kind of very scientifically correct, but I like to describe it like a shortcut. Instead of, if you create a variable and you put information there, to my mind, it's like duplicating a file in your folder, in your hard drive. But if you create a pointer, it's more like a shortcut or I think in Windows it's called a shortcut to a file, or in Mac it's called an alias to a file. So it's pointing the way to the source. Instead of duplicating information, you're just creating kind of a wrapper that points you to the source. So that's what we need to do. We need to say float, and then you create a number, you create a name of a float, and then you say equals the n bands. So let's do that. Float, and I can say that we can't forget the asterisk, which is the kind of the indication that we have a pointer. We can say float my spectrum, for example, equals of sound get spectrum. And for the number of bands, we can use this integer that we created called n bands. And this, it kind of creates kind of an array, right, with size 512, and each of these items in the array will have the value from 0 to 1 of that frequency range or that frequency band. Okay. Okay, this is great. I can now draw rectangles. So how many rectangles do I need to draw? N bands of rectangles, right? So let's create a for loop, and the for loop goes from int I equals 0 to I lesser than n bands, and then I plus plus, right? Great. So now we can draw some rectangles, okay? So I can say let's define the position for the pos x for each of these rectangles. So I can say integer, or not integer, I'm just going to call it float pos x. We're going to map the I to the screen of map, so that we have these rectangles across the screen. Pos x is of map, we're going to map I goes from 0 to n bands, and we're going to map this to 0 and of get width, right? So then we distribute the rectangles through the screen. Okay, so we have the position x of the square of the rectangles. Now what I want to have is the height. What is the height of the rectangle? So it's going to be the float times the height, right? The height of the screen. So I can say float height is gonna be the spectrum, the information from the spectrum array, right? Spectrum I times of get height, because if that frequency is in the maximum, the bar will be sorry, my spectrum. I didn't call it spectrum. I called it my spectrum. My apologies. If that frequency is very loud, the bar will be the size of the screen. So of get height. If it's very low, it's going to be close to 0. So we have the position. We have the height. So basically, we can draw our rectangles, right? We need the width. So the width is the width of the screen divided by n bands, right? So maybe logically I should have width before the height, I think. So I'm going to add it here. Width equals of get width divided. So then we have the contiguous bars divided by n bands. And we are almost done. Actually, I don't need this float width inside the for loop, because it's not depending on I, right? The position is, the height is depending on I, but the width is not. So I don't need it to be calculated 512 times, this width. It can be calculated only once per frame, and that's about it. So if I have that, I can now say of draw a rectangle, and the float x will be pos x. Let's draw for now the rectangles in point 0. We're going to see that this is not very nice, so we're going to invert it, but for now let's keep it in point 0. Float w is my width, right? Width, and float h is my height in this case. Okay, so we've done all this work to build our bars, right? So let's see how it looks. Do we have everything right? So one thing, well, it compiles. Let me explain that. We get of sound get spectrum gets all the spectrum of all the sounds currently playing. So you can't just analyze. There we go. So a few things I like, a few things I don't like. So let's discuss. So this, the leftmost information is the low frequencies. Here we have the mid frequencies, and there's not much high frequencies going on in this song. Here clearly you can detect the tambourine, right? The guitar is more or less here, right? And the guitar and the snare are more or less in the same frequencies, and the bass drum and the bass are more or less in the same frequencies. If we pay a bit more attention, we'll probably be able to identify that. Then, as you know, there's the harmonics, right? When you have an instrument, there's not just there's the main harmonic, the main note. In the guitar, this is quite clear. There's this kind of ghosting. The pattern of the guitar is kind of repeating across different frequencies, which is okay. That's normal. Another thing that is quite common in FFT analysis is there a lot of prevalence. So the information in the low end is much more condensed. It's much more close together than the information in the higher end. That makes this information much louder. And I always like, when I do FFT analysis, I always like to have some kind of a little adjustment to create more dynamics in the mid-high area. Okay, so let's... Also, another thing I don't like is that it's drawn from top to bottom. I'd rather have it being drawn from bottom to top, and more of a graphical kind of standardized graph kind of thing, right? So let's address all these issues one at a time. So to put it, let's start with the last one. To make it draw the other way around from the bottom, the rectangle needs to be drawn from of the height, right? And then it needs to be drawn, height needs to be inverted. This needs to be inverted so that the bar goes up, not that. Otherwise, it's being drawn in the bottom of the screen and being drawn downwards. We wouldn't see it. But if I invert the height, then it's gonna go up to the top of the screen. So let's take a look at that. Yeah. Other things I don't like the color palette of this. We could change the color palette. And we have a for loop with the end band, so it would be very easy to map a color here. So for example, let's say that offset color. And we could map, for example, the red. We could map the I that goes from 0 to n bands to a color range, which is from 0 to 255. So this is red. And then maybe I leave green in 0, and maybe I put blue in 255. So we have these kind of purples and this kind of range. So I could have created a red variable just to make, but I think it's clear and it's kind of compact enough. It doesn't create I don't like very long lines of code. If I have a big line of code, I divide it into variables or things like that. That it becomes more clear. So now it's nice. We have this kind of blue becoming a purple, magenta kind of color, right? As it goes along the spectrum, so it's a bit nice. And since we're talking about color, maybe a black background would black always improves anything. So there you go. And we're almost there. Now, this compensation mechanism that I was telling about. So, how I compensate for this? Basically, usually I compensate. I multiply the spectrum times I. So if we then the higher frequencies will get amplified by I. But you have to be careful, because if you multiply by I, then the first frequency will disappear because the first I is 0. So usually I multiply this by I plus 1. times of get height. So let's take a look how this would look like. So it creates kind of a compensation mechanism to make the higher frequencies look taller somehow. So it creates more dynamic, you see. Now it's a little bit messier. I mean, it's a matter of taste. You can adjust these values. Instead of I, you can have I divided by 2, for example. Also, you can change the num bands to something like 32, for example, something a bit smaller. Let's take a look how it looks like. Better, no? I think it looks a little bit better. So here you can, again, you see the guitar. I'm trying to spot the snare. It seems to be here where I have the cursor, the snare, but I'm not entirely convinced yet. Need to spend more loops. Clearly this is the tambourine, right? Now it's very clear. And now this is really useful because, you know, you can create a lot of procedural kind of behaviors based on this. So you can say that, you know, you want to map this frequency. So if you have 32, for example, that we're in the middle, so this is probably 16. You want to map information from band 16 to the circles. You want to map information of band 0 to the squares. And you can map this to a particle system or something like that, so that you can create kind of interesting dynamics here. And that's basically it. I mean, we could tweak this a lot, but we can discuss more in class how we could do it according to your preferences. And that's it. This concludes this version of this exercise.